Hey everyone, today we're talking about tree walk interpreters. Previously, we've been talking about parsing a whole lot, which is going from source code to abstract syntax trees. And more recently, we've talked about semantic analysis, which is going over this tree and checking properties of interest. As we'll see today, there is also a secondary role for semantic analysis, and that's to collect some data that might be useful while either generating code or while running the interpreter. In my videos on semantic analysis, I went over my own implementation of semantic analysis in my demo language, and we had to deal a lot with trees. So we walked the tree to create rules that were then used to derive attributes, and these attributes were used for checking properties. This will be useful because once again, we're dealing with a tree and you want to traverse the tree to perform the actions that correspond to the tree's node. So as you can see, there's no interpreter in this pipeline. So it's a classical pipeline where we emit code, but we can replace it by an interpreter here. And this is only one of many possible designs. We could have a tree walk interpreter, or we could have another form of interpreter, which is a bytecode interpreter, okay? And that's commonly called a virtual machine. And really, when you think about it, when you run what we call machine code on your CPU, actually, your Intel or AMD CPU itself, it's interpreting the machine code, because what it actually runs in the hardware gates, which you might have seen in your computer architecture class, what it runs there is microcode, so it's not actually machine code that you're emitting. So you might be wondering, what's the difference between a tree walk interpreter and a bytecode interpreter? Well, the tree walk interpreter walks the tree as the name implies, and the tree more closely matches the source and the structure of the source. Whereas a bytecode interpreter goes over a series of instructions, okay? And such a series of instructions are necessarily linear. So you need to have transformed this tree into this linear representation of instructions that are executed one after the other. There are also jumps, of course, when you do function calls and when you have conditionals. So when should you use a tree walk interpreter? As we've said before, tree walk interpreters or AST interpreters, they are slow. Okay, and that comes from the fact that they do a lot of megamorphic call. We're going to talk a bit about that later when we talk about optimization. And another reason that they're slow is due to their very nature. So when you're writing an AST interpreter, you want to manipulate the data you already have, and mostly that's the AST and some extra data from semantic analysis, to just execute the code as fast as possible. And when I mean as fast as possible, I'm not talking about performance, I'm talking about simplicity of the implementation. You don't want to go through a lot of contortions that will help you generate stuff that will make the interpreter run faster. Because if you start generating a lot of data structures that will help the interpreter, then that begs the question, if you're doing all that, then why are you not really emitting bytecode and writing a bytecode interpreter? These are the two extremes of the trade-off. Either you generate nothing or as little as possible, or you generate as much as you can, and in that case you have a bytecode interpreter. And I would say there isn't really a trade-off here. So picking something in the middle where you generate a little bit, it's not that useful. Either you do an interpreter because you don't need speed and you just want your code to be simple, or you do a bytecode interpreter because you do want speed. Or you could also generate machine code directly. So why write an AST interpreter? Well, sometimes speed is not the key consideration. Okay, often they're good enough. And that's typically the case for domain-specific languages. So not a general purpose language, but a language for queries, a language for parsers, things like that, things that are not going to run all the time, and it's okay if they're a bit slower. Computers are fast. What that buys you is developer time. And often that's the most precious resource that an organization can have, is the time for its developer and also the happiness of its developer. And such code being simpler is also easier to maintain. So not only does it buy you developer time now, but also it buys you developer time in the future over the long term. It can also be useful for general purpose languages. Once again, the benefit comes from the fact that it's faster. So if you want to explore the language design, it's easier to change the AST interpreter than it's to change the whole code generation. And so your iteration time is faster. It's also good for testing your language, because say you start by writing an AST interpreter, and then you go to write a bytecode generator. You can compare both your implementations. And as a sidebar here, any form of testing is rooted in redundancy, okay? So with the two implementations, they are redundant because they're doing the same thing. But when you think about it, when you write unit tests, you're testing your implementation against some input and output, and the output comes basically from you computing in your mind what the answer is. Or maybe you might be using a simple, naive, partial even implementation, and using the simple implementation against the real implementation to verify that, at least in simple cases, they do the same thing. To summarize, AST interpreter, often they're good enough, they buy you developer time, and they're a great tool for iterating on the language design and to actually test your language.
In the rest of this video, I'm going to give you patterns and insights on how to write interpreters. Writing tree-walk interpreters is actually very simple. In my demo language, semantic analysis is about 1000 lines of code, and the interpreter is, I think, a bit more than half that. So it's less code, and also I think conceptually it's much simpler. It's simply a matter of walking the tree and executing instructions as we go. The first thing we're going to see is how to write interpreter for expressions. So we have this AST whose root is expression node, and you have two classes extending this node. You have integers, which are simply wrapper for integer values. You have sum, so there's a left and right component, and a product as a left and right component. So the behavior that we want is that when we evaluate the integer literal, we want the integer. When we evaluate the sum, we want to evaluate left and then evaluate right and return the sum of the evaluated integers. And when we visit the product, we want to evaluate left and right and get the product to that. This is not functional code. See, there's the little red squiggles. And that's because when you say you want to visit node.left as type expression node, that means it could be any subclass of the node. It could be a literal, it could be a sum, it could be a product. So which one of these methods do we need to run? You need some kind of dispatch to determine that. And we're going to see two methods in which we can do that. The first is the very classical visitor pattern. So you might have seen this in another course. So we start by defining a method that accepts something called a visitor, and we shall see what that is. And we implement this method in every subclass, and the implementation is always exactly the same. Return visitor that visit this. The trick here is that this has different types in different implementations. So in this implementation, the type of this is integer node. In this implementation, it is sum node, etc. And so this will help pick the right visit method. And remember, these are the visit method. And by the way, they don't need to have the same name. So you could have called this literal, you could have called this sum, you could have called this product, and it still would have worked, provided that you change this by literal, you change this by sum, you change this by product, of course. It's just convenient to always use the name visit. Makes it a bit simpler, you can copy paste the code, but make sure you understand what is going on exactly here. The next step is to actually define the expression visitor interface and to have it implemented by the interpreter. And so basically it's the same methods that we saw before, except that we don't call visit here, we instead call node.left.accept directly, with this being the interpreter, which is an instance of the visitor. If you only ever use the visitor interface for a single thing for the interpreter, then you can get rid of the interface and you can just use interpreter here directly, but typically it's a bit cleaner to do it this way. And then we can test it in the main method. So we build here an AST that is an AST for 1 times 2 plus 3. And then we can accept the interpreter for this expression, for this node, and you can try it out. I will put a link in the description and see that indeed this does evaluate to 5. Now, another way that you could use to write a three-walk interpreter is to use something I called dynamic lookup. In this case, we're going to use this class called valuedVisitor, which is a class I defined in my utilities library. It takes two type parameters. The first is going to be the top type for the nodes, and the second one is going to be the type of the result of the visit operation, right? So here it's int, so it should be integer. And we're going to register for each type of node the method that we want to call. Okay, so this integer is going to be that sum. In this case, we could have called them with the same name, so we could have all called them visit, and through the magic of generics, this actually would have worked. When you get it wrong, however, the error messages are a bit confusing, so I really like to have different names in this case. It makes it much clearer. And this method here is just a simple helper method. Something I'd like to draw your attention on is that this is different to what we did when I showed you my implementation of semantic analysis. In semantic analysis, I used also a utility class, but this class automatically derived the order in which it had to visit the tree, and it actually visited all the node by itself. Okay, so it would do a pre or a post visit, so it would visit the parent node, then it would visit all the children node, and then it would call another method on the parent node again. And it would do all this by itself. In the visitor, that's not the case. Okay, so by default, it's not recursive. If I don't call visit here, in sum, it's not going to visit the children. I need to do it explicitly. And I want to be doing it explicitly because I want to control if and when the children node are being evaluated. So we're going to see this later for the if statement, but in the if statement, I want to evaluate the if part only if the condition is true, and I want to evaluate the else part only if the condition is false. And I certainly don't want to be evaluated both parts in every case. I have to choose. So we can test this here, and again, we just build an AST node for 1 times 2 plus 3, and you can also verify that this works. So which should you use, the visitor pattern or the dynamic lookup using some utilities? The visitor pattern is usually much faster, so for a real language, I would go with that. Dynamic lookup is slower, but that's good enough if you're just prototyping and you don't care about speed. And there is a little bit less ceremonies, or a little bit less typing to do, so I typically like it better when I'm just at the stage where I'm playing with a language. And the reason why it's slower is that you need to take the class of the node that you want to visit, and you need to look this class up in a map, so that's quite slow compared to just doing one virtual call. Dynamic lookup has another advantage, is that it's extensible. So say that you're publishing this visitor as part of a library, okay, and someone else, a third party, is using this library. This third party can register handler for new subclasses, so in this case, new types of node. If you are using the visitor pattern, for the visitor to be able to handle new types of node, you would need to edit the visitor interface and also the interpreter class, and these are part of a library, so you can't actually edit them. This is an example of a more global problem called the expression problem. What the problem says is that languages paradigms, they typically make it easy to either add new data variants, so in this case there would be new kinds of nodes, or they make it easy to add new operations on the nodes, but then it's hard to add new nodes. So one of those two things is easy, otherwise it's hard. So you can look that up if you want, it's quite interesting. And so this dynamic lookup, it's a way to work around this issue that you have in languages. Our next step will be to add statements to our interpreter. So in particular, I'm going to add two new kinds of statements, a if-else statement, which as a condition, a if true part that's going to be executed if the condition is true, and if false is going to be executed if the condition is false. And then a print node statement that's just going to print whatever the expression is. So the implementation is as follows. For the if-else, we interpret the condition, so we visit it. Our language only has integers so far. So what we're going to do is we're going to say if the integer is 0, that's false, and otherwise it's true. So we actually do that. If the condition is not 0, we visit the true part, otherwise we visit the false part. Like we said before, we only visit one of those two at each point, depending on the condition. For print statement, we just use system.out.println, and we evaluate the expression and print that. So you'll notice that this function returns an object, and that's because the expression are still part of this interpreter and need to return a value, an integer, okay? And we've changed the return type for all visitor method to object. That's why we're forced to do a cast here, okay? We know that the expression is always going to be an integer, but the type returned by the visit method is going to be object, so we need to cast. The statements do not evaluate to a value, at least in our language, and so in this case we just return null for these two statements. I also changed the top type for the AST to node. Okay, it used to be expression node, but now we have statements, so expression node doesn't cut it anymore. We can test this. So we build a node for true and false when 0, and then we said if true, print true, else print false, if false, print true, else print false. And we run these two statements, and indeed, when the condition is true, we print true, and when the condition is false, we print false, so it works. So a little comment about what I did here. I changed the top AST type to node, like I said, so now everything extends node. This is fine, but it's not ideal, because I can write, if I want, something like that, and the system that we have will let me do that. So if print true, true, false. We certainly might want to restrict the condition so that it's always an expression. Remember that this is a statement, so this will, when evaluated, will return null, so the if-else node will crash, because it will try to cast null to end. Okay, so we don't want that. And in some languages, only statements are allowed to be in a if-else, so that depends on your language, but we might want to add this restriction also. So how would we do that? Well, we would create some abstract classes called expression node and statement node. And these will inherit from node, which will still be the top type. And then the statements would inherit from statement node, and the expression would inherit from expression node. What this would allow us to do is introduce restrictions. So in the definition of the if-else node, for instance, we would change here the type node by expression node. And maybe we would also change the type of these two nodes by statement node. So that's just a bit of added type safety, which makes it harder to make mistakes, basically, in your compiler. Another thing to note is that this is an example, and it actually doesn't check things that you want to check. So like I said, here, either you want to guarantee in semantic analysis that the condition is always going to evaluate to an integer, and then this can never crash in the interpreter, except if you made a bug in the interpreter, of course. Or you want to check that the value returned by this is indeed an integer. And if it is not, then write an error message to the user that's going to tell him what's going on. Because otherwise, what you will get is a class cast exception from the interpreter directly. And typically, it's going to be very hard for him to interpret. In particular, he will not know which part of your program that comes from. He will only know where it is in the interpreter. All right. So the next topic is how to implement scopes. And I'm going to show you a very simple way, a simplistic way, which is actually not a great way to implement scopes, but it will give you the simple idea. Then I will give you the reason why it's not such a great idea to do that. And I will explain how to do it better. I will not show the code because that would take us into the woods a bit too much, but I did implement it the right way in my demo language, and I will put the link to that in the description. It's the same GitHub repository as before. So I added two new nodes, a setVar node that assigns a value to a variable, and a varref node that reads a variable. Okay, so there's, in both cases, there's the name of the variable, and for setVar, there's also the value that we assign to the variable. I also created a new scope class, and this scope class is just a map. Okay, see here, hashmap string object. So we create a new version of the interpreter, and here I did something fancy. So interpreter 3 is the last version of the interpreter, is the one with if and with print. And that one was all new, because remember we changed the return type of the visitors, and we changed the top type of the AST, so we couldn't extend the previous interpreter. But now, we're not changing these things, so we can extend it. And this is only possible because we're using the dynamic lookup method. So the previous interpreter is as a visitor field, okay? And if we extend this class, we can access the visitor and add new handlers for the new nodes. So this is the kind of things that you can do with the dynamic lookup method. And like I said, in general, you wouldn't want to use that, but for prototyping or examples in this case, it's quite useful. So let's go to the implementation of the new nodes. One very important thing is that for scopes, we need to get information from semantic analysis. So we actually need a reference to the reactor. Once we have the reactor, we use that to look up the scope for the nodes. Okay, so this needs to have been set during semantic analysis. So we get the scope for the setVar node. And basically, since the scope is just a storage from string to object, we just use it as a map. So we do scope.put, the variable name, and then the evaluation of the expression. For the variable reference, we also get the scope, and then we just look it up in the map. So think about it for a few seconds. What's the issue with this way of doing things? And I will give you a hint. It has to do with the scope. Okay, so the issue is that the scope is shared between semantic analysis, it's created during semantic analysis, and the interpreter. And this has a few issues, and we'll see what in 30 seconds. But first, we need to try out if what we did is correct. So we create the reactor and the interpreter. We create a few nodes, so true, false, reference to x, setting x to true, so true is 1, and setting x to false, which is 0. Then we need to do semantic analysis, but we haven't implemented semantic analysis here, so I'm just going to simulate it by just setting the attributes directly in the reactor. So basically, all the nodes are going to use the same scope because it's the same variable. And so for set true, set false, and x, I set the scope to a new scope. Then I run the interpreter on all these statements, and this is the same interpreter instance, so the scope is going to be the same, and it's going to read and write the same values. So I set x to 1, then I print x. As we expect, the value print is going to be 1. Then I set x to false, then I print x, and as expected, the value print is going to be 0. Okay, so as promised, why is using these scopes a bad idea? The main issue is that if you have recursive functions, there are going to be multiple instantiations of the same scope. So say you have a recursive function called foo, and it has a variable x, and foo calls itself. When you enter the body of foo for the second time, there's going to be two versions of x, the versions of x that's in the first call and the version of x that is in the second call. If you write in the same scope, you're going to overwrite the value of x, which is going to make your program incorrect. And typically you want to have recursive function calls, so this is always a bad idea. Another more philosophical reason why you don't want to do that is that if you reuse this object from semantic analysis in the interpreter, you are strongly coupling semantic analysis and interpretation. And that means that you can't, for instance, reuse the results of semantic analysis to run the program multiple times. So you need to redo the compilation each time, which is not optimal. And there's no reason to couple your design like that. What can we do then to implement scopes in a way that is realistic? So first of all, we decouple. So instead of writing in the scope directly, we create a new kind of object. I'm going to call that scope storage. And each time we enter a scope, so that's going to be usually a block or a function body, we create a new scope storage. Each scope storage is mapped to a single scope, but there can be multiple storage for a single scope, right? Like each time you enter the same function, you're going to have a new storage, but the scope is the same. So just like scope, storages are nested, and function calls reset the nesting. What does that mean? It means that when you call a function, you don't want to access values that are in the body of the function that called it, okay? There are actually some languages that work like that, but unless you've written some Emacs Lisp, you've never used them. And it's a bad idea. How do we implement lookup in these storages? So first thing, you get the scope for the node, and the scope was computing during semantic analysis, so that's how we start in the example that I showed you as well. And then we traverse the nested storages. Remember, we keep them in the interpreter as a linked list, basically, from inner to outer. And so we traverse these nested storages until we find a storage that matches the scope. And once we found the proper storage, then we can read and write the variable there. There's never going to be a conflict where we could find the wrong storage, because that would come from a previous function calls. And like we said, function call reset the nesting. So like I said, I implemented this in my language, and you can go check that out if you want the nitty-gritty. But here you get the general idea. So there are two pitfalls that we need to address with this method. First pitfall is having some kind of global scope. Because we said that making a function call resets the storage, you can't access the global scope. And so if you want to have a global scope, and often you might want to, if only to provide some global functions or some global variables that can be useful, then you need to code that explicitly. You can't use the same normal mechanism that goes through all the nested scopes. So typically what it's going to look like is that you're going to look up the variable using this nested storage mechanism. And if you find nothing, then you're going to look in the global scope. You can also store the scope object for the global scope and just compare that directly, for instance. That's what I do in my language. The second pitfall comes from a language feature called closure. So this is an advanced feature. Your language will not necessarily have that. But if you want to have closures, it's going to be an issue with the way that we've described. So what are closures? Closures are a nested function that capture outer variables. And I gave a Java example here. So we have this function called foo. We define a variable that's the integer 42. And we create a lambda function, which is a supplier of integers. So basically this function just returns x. But x is not defined in this function. Okay, it's not defined in bar. It's defined in foo. So we have a reference here to the scope of the outer function foo. So what a closure is that it's an environment, and environment, you could say it's a scope storage or some kind of storage for values that are captured, and a function. So this function is always the same, but x changes. And each time you call foo, you create a different instance of bar. Each time you call foo, bar is going to be different. It's a different instance that refers to x. This is a bad example because here x is always 42, but you can imagine that x is a parameter of foo. So each time you call foo, you're gonna create at least a bar function that returns a different integer. Say you want to have closures in your language, and they are quite a powerful programming tool. How do you do that? In Java, closures can only be read-only, okay? So you cannot write to x here. And please ignore this code. This is for the next point. But you can't write to x. At the time where you create the closure instance, so at the time the instance for bar is created, you need to collect all the values that are captured. So in this case, there's only one captured value, that's x, and store them in this new environment object that you're going to create. And then the closure becomes this pair of this new environment and the function is always the same. And basically, what happens is that the function has a hidden parameter, and this hidden parameter is the environment. So that's how to do it if you only want to read from capture variables, like Java does. If you want to also write to capture variables, you're going to do something similar, but this time it's not enough to just capture the value. You need to be able to write. And that means that you can't store in the scope storage the value directly. Instead, you need to store a wrapper that allows reading and writing. So this is a bit abstract, so let's look at an example. This is invalid Java code, because as I said, you can't write to capture variables in Java, but let's assume that we can. What does it look like? So this time we don't have a supplier, we have a runnable, and it captures X because it's going to print X, and it's also afterwards going to write 0 to X. And so what we're doing is then we're running this bar function twice, then we're assigning 43 to X, and then we'll run it again. So what will happen? First time we run it, X is going to be 42, so we print 42. Then X is going to be set to 0. Then, so this will print 0. Then we set X to 43, so this is going to print 43. So as you can see, there is a bidirectional interaction here. Like when we write in the function, this will affect. When we write in the function foo, it will affect the function bar, and when we write in the function bar, it will affect the function foo. So the value of X is propagated between both. It is really a shared variable. If we had just captured the value of X at the time when bar was created, what would have happened is that the first time we would have printed 42, then we set X to 0, assuming that's allowed, and then afterwards we'll always have printed 0. This would have printed 0, and this would also have printed 0 because changes to X in foo would not have been reflected in bar. So we really need for X actually to be a wrapper object that allows reading and writing. And similarly, when we read and write in X, we don't need to read and write to the scope storage. We need to read and write to this wrapper object. For the last part of this video, we're going to talk about some other tips and techniques that you can use to write AST interpreters. So the first thing you should start doing when you write your interpreter is to define the data representations that you're going to use for your languages. So to take an example, if your languages has arrays, how are you going to represent them? Are they going to be Java arrays, or are they going to be lists, collections, something like that? If your language has null, is that going to be the same null as in Java, or are you going to create a class called null and create a singleton that's going to represent null? It will depend what you need to do with this data. Different languages have different requirements, but you should think about it. One thing you should pay particular attention to is polymorphism. So polymorphism is whenever you have a variable or a value that can have multiple types, or rather like a variable that can have values of multiple types in it, for instance. So just to give you one example of that, if your language allows arrays that can contain values of multiple types, are you always going to type arrays as array of Java objects? Or do you sometimes optimize it to say an array of int when your array only contains integers? That's probably a bad idea, unless your arrays are immutable. Because if they're not immutable, it means that you can take this array that only contains integer, and at some point you can go and write, say, a string in it. If you try to do that to int array, it's not going to work, obviously. So this requires careful consideration. And in general, all cases where polymorphism is involved, you should pause and think about what could happen here and make sure you cover all the possible cases. So to give you some more specific tricks, how can you implement control flow? Things like return, break, continue. So let's take return, for example. When you encounter a return statement, you must stop executing instructions in the function where you are. The thing is, these statements are probably being executed from a loop in the function body. Okay, how to communicate to this loop that it should stop. There's a multiple way to do it. One way would be to have a flag that the return statement would set to true, and then the loop would check on each iteration if the flag is set. There is a simpler way when you write an interpreter in Java, and that's use exceptions for the control flow. So that's what I do in my demo language. There's a performance trick here that you can use. Throwing exception in Java is pretty cheap. However, there's one thing that's very expensive, and that's building the stack trace. It is possible to avoid building the stack trace. So look up the, I don't know if it's exception or throwable class in Java. There is some constructor parameter that you can use that will make it not build a stack trace, and that will make exception much faster. This is not a crucial consideration. Like we said, interpreters are inherently inefficient, but it could make the difference in your use case. So I've said this also multiple times, but if your language is dynamically typed, don't forget to perform type checks in the interpreter. Otherwise, your user will be faced with confusing exceptions that it will not know what to make of. Finally, how do you implement function calls in the interpreter? So what you want to do is that during semantic analysis, you're going to map the node that calls the function to the node that defines the function. If you use the Uranium library, that means that you are going to set the attribute on the call node to point to the definition node. I think in my language I call this attribute decl or declaration, something like that. So once you've done that in semantic analysis, what you need to do in the interpreter is when you're visiting the call node, you will do two things. First, you'll create a new scope storage for the scope of the function. And that's what we typically call a stack frame, okay, where the parameters and local variables of the function live. And once you've created this scope storage, then you're going to visit the node for the body of the function, okay, and you get this node from semantic analysis. So once again, this is what I do in my language, so you can check that for the details. And that's it for this video. Next time we're going to talk about Java bytecode. Take care, and I'll see you all next time.